Okay, so let's start. First, thanks everyone for coming to this talk. Especially many of you may already know this classic topic a lot. So I'm here just want to summarize the community effort and for generalized linear model features in Spark. And this is a community effort. It's not the work done by myself. It's a joint work with many contributors like Joseph and Eric from Databricks, and Yanbo from MLlib, and also DB from Netflix, and some other contributors from the community. So first, about myself, I'm a software engineer at Databricks working on machine learning and data science. And I'm a Spark PMC member. I'm also a maintainer for the MLlib component and PySpark component. I did my PhD at Stanford, and my thesis work is on some randomized algorithms for large-scale linear regression problems. We're not talking about the randomized algorithm today, but it's kind of still related to my research topic. So I'm happy to present the linear models here. So in this talk, first I'm going to make a really quick introduction about the linear models. And let's maybe do a quick survey here. So how many of you already know generalized linear models, like link functions and distributions? And how many of you are R users? Oh, great. So, and then I will talk about how to use generalized linear models in MLlib and SparkR. I will just give a demo and a quick demo about R formulas on Spark. And then I will go to some technical details about how we implemented generalized linear models in Spark. And first of all, let's talk about the linear models. Actually, it's very simple. And look at it. I took this chart from Wikipedia, and you were given a list of points to the space. And you want to figure out what's the relation between the x values and the y values of those points. And you try to just formulate a model to interpret it. And if the model is linear, let's assume that there is some linear relationship between the x values and y values. You want to fit the points with a straight line. And that's the linear model between x values and y values here. And usually you care about the model itself. What's the slope of this line? And that means if I move x values to the right by maybe 3 units, how much increase I should expect in the y values. That's usually called model inference, and you want to estimate the model parameters. Another important application for doing these linear models is for prediction. And you want to use these models. There are just coming records. There are some values coming in on the x-axis. And you want to make predictions about what the y values should be. And that's also very important use cases. And so let's start with the simplest linear model out there. That's called linear least squares. And basically, you have some observations from your training data set. And you see this x1, y1, x2, y2. And x is a vector, and that indicates some features, and y is a scalar variable, and that indicates the response. So for this linear model, we assume there's some linear relationship between x and y. So you can express y as x transpose beta, some coefficients, you need to estimate, and plus an error term we call epsilon here. And in order to estimate this linear model, you want to just define objective and then minimize or maximize this objective. And here, we just use the simplest approach. Just take the sum of squares of the errors. And that's the formulation given at the bottom. And I believe that everyone has seen this formulation. And this is perhaps the oldest linear model out there. You can trace back to the great mathematician Gauss. And it's also the simplest and most started linear model. And the best thing about it is it has an analytic solution. And it's very easy to solve. I mean, relatively easy if you compare it with the models we're going to talk about later. And it's also very easy to inspect. You look at the coefficients. Every coefficient maps to the original feature. And then you know that if you look at its coefficients, you know how important the feature is. And relative to the response variable. And however, it's kind of sensitive to outliers. And because we use this L2 squared distance, and if you have an outlier, you may pull your model estimates by just far from the real estimates. But that can be fixed later by introducing some regularization terms or switch to a different model. And that's the model for regression. And we also care about classification. And the simplest one is logistic regression for binary classification problems. And here, the difference between the regression problem is the response variable is taking some discrete values. For binary ones, it's taking values from 1 or -1. And it could be, in your implementation, it could be just a true or false. And it could be just a user click on some ads, or the user just ignored it. Or someone likes a movie or dislikes a movie. So for this one, and people use logistic function to indicate the likelihood. And it's 1 over some 1 plus some exponentials. And essentially, if the inner product between x and the coefficient beta is large, and then this value is very close to 1. And if it is very small, and this value is very close to 0, and you can look at this graph here. And so to estimate this model, we maximize the sum of the log likelihood. So basically, what parameters give me the most likely model here? And it's equivalent to the formulation at the bottom. And we did some equivalent transformation just to make it simple. And for logistic regression, yeah, it's the simplest binary classification model. And it's widely used in industry. And people use it for CTR predictions. People use that for recommendation. And people use that for really large production deployments. And because it's still relatively easy to solve, harder than linear models, but still convex and smooth. And it's very easy to interpret because you can also map the coefficients back to the features. And that applies to all linear models. And that's for binary classification. We can also solve it with just for multi-class problems. And here you take the response value to taking values from some discrete classes like 1 to k. And we can use a similar technique here to indicate the likelihood. It's called softmax. And to estimate the model, we try to maximize the sum of log likelihoods. And you get a very similar generalization. It's good generalization to the logistic regression in the binary case. And those are some common regression models and classification models we usually use in practice. And though the formulation looks quite different, they fall under the same framework called generalized linear models. And they could be specified by error distribution of the response. And usually this is taken from an exponential family. And also a link function that maps the mean of the responses and to the inner product of x and beta. So to estimate a generalized linear model, we try to just maximize the log likelihood, the sum of log likelihoods. And here in the formulation, and basically you're given xi, and given the current beta, and you want to estimate what's the likelihood of yi equals to the observed value. And here I want to list a few just common distributions and link functions for generalized linear models. And we have, if the distribution is normal and the link function is just the identity function, and that corresponds to the linear least squares. And if you switch to binomial and the link function is logit function, that's the inverse of the logistic function. And that maps to the logistic regression problem. And also it applies to multinomial logistic regression. And then there's Poisson regression and gamma regression. And if you change different distribution and the link functions. And so basically, once you understand your data, you know, well, what kind of error distribution you want to choose. And then use that distribution and then pair it with a link function and see whether it fits your data really well. And that's how people use generalized linear models in practice. And in this talk, I also want to talk about another linear model that's very similar to those linear models we introduced. And it's called accelerated failure time model for survival analysis. And in survival analysis, you want to estimate the lifetime of maybe some subjects. And you also have observations like X and Y. Here, X are just some features, and Y is the observed lifetime. And there's an extra column, C here, indicates whether the subject you observed is still alive or already dead. So basically, if it is already dead, and then the lifetime is the true lifetime. And if the subject is still alive, and that means the lifetime must be greater than the observed lifetime. So that's a additional column in your input. And we use this accelerated failure time model, and basically it means if you change the value in X, and then it will accelerate or decelerate the lifetime by some constant. And with some certain constraint, this just specialized the model into a log linear model. And that's very similar to the linear models we introduced, but just replace the variables by their logs. And we also use max likelihood and to estimate this model, and by just treating the instances differently, whether it's censored or not, they have different likelihood. So for this model is one of the most popular models for survival analysis, and it's a parametric model. There are also popular non-parametric models and parametric models. And this definitely will just widely used for lifetime estimation. You want to estimate how long your user will subscribe to your service or some customer churn analysis. And I'm not just an expert on survival analysis. I know more on the implementation side. We picked this model because it's popular and it's also very easy to implement on Spark. We know how to implement it because it's just using the same framework we use to solve GLMs. But if you have, just better algorithms or just certain applications that requires a different model, maybe just let me know offline. Yeah, so in practice, when you use those models, you don't use the basic formulation. You make certain modifications to the models. And usually, well, this is the objective you use in practice. And the difference, let's look at the differences. The first one is the WI. That's a multiplier in front of the log likelihood for each instance. And this is the instance weight. And think about, in some cases, like in an application, you get some explicit feedback from users. They click on your items and they like your movies. And that's very confirmed that that's a positive instance. But sometimes they don't do explicit feedback for negatives. And you get some implicit feedbacks, like they just ignored that item from the search result. It could be a negative, but you are not sure. So basically, you don't want to put the same weights as a positive instance. You want to change the weights in model fitting. And then you use this W here. And inside the log likelihood function, we also have the beta 0. It's basically try to adjust the bias of your estimate. And otherwise, think about the chart we showed initially, and the line must go through the origin. It won't fit all the models. And this is the beta 0 term, and it's just called intercept term. And also on the right side, we have this regularization term. And it's very important to avoid overfitting. And because you don't want to just let the beta to be arbitrary values, you want to control the values such that you know that the model should be reasonable. And then lambda here is to control how much weight you want to put on the regularization term and how much just to make a balance between the loss function and the regularization. And usually, and this is done by lambda is normalized by the number of instances in your training data set. Here is just normalized by m to get a good balance. And there are many types of regularizations. And in MLlib, we support L2. It's also called ridge regression, ridge regularization. And essentially, it's just the square norm of the two norms. And it's very easy to solve with the L2 regularization because it's strongly convex. And then we also have the L1 regularization. It's called LaShu, very popular model. And it can help you to enhance the model sparsity. Basically, you get a smaller model, and it's easier for you to interpret. And also, sometimes it provides better generalization errors. However, it's harder to solve, definitely much harder than the L2 case. And it's still good to solve because it's still convex. And we also support a regularization type called elastic night. And that's a combination between L2 and L1. And there are definitely other types of regularizations, but we don't support that in MLlib. And so next, I want to show how you can use generalized linear models in Spark, and especially in MLlib and SparkR. And those linear models are implemented as ML pipeline estimators. I don't want to go into the details about ML pipelines. And essentially, estimator takes an input as a data frame. And inside the data frame, you have just different columns. You may have one column containing the features, one column containing the labels. And then the estimator will take the training data frame and then train a model. And the model can be used to apply to similar data frames with similar or the same schema to make predictions. And that's what we call a pipeline. And they accept the following just common parameters. Like you can set the feature column name, and you can set the label column name. And optionally, you can say, I have sample weights in my training data set. Then you can set the weight column. And you can specify the regularization type, like L1, L2, or elastic night. Or you can control the regularization param. That's the lambda in the previous formulation. And you can choose whether to fit intercept. And also, each algorithm has their own special parameters. And you can just look at the user guide. And yeah, this is how you fit a linear model in MLlib. It's pretty simple. First, import the classes. This is Python code. And then you read some training data from external data sources. It could be Parquet, could be CSV, or could be libsvm. And then you load them in. You construct a logistic regression instance. And for example, you have this specify those parameters, like whether you want to fit intercept, how many number of iterations you want to use. And then you just call logistic regression.fit on the training data set, you get the model. And then after you have the model, you definitely want to make predictions, right? So you just load the test data set, and you call model.transform on the test data set. You get the predictions. And then you can use, if you want to evaluate how good your model is, and you can create a binary classification evaluator because you're using a logistic regression model here, and then to get some evaluation metrics out from the test data. So it's very simple to use. And this is for the Python API. And we try to make the Scala API and the Java API the same or very similar to the Python API, just to keep the consistency. But however, for our users, we took a different approach. So we try to make the API as similar as possible to existing ones in R and some popular R packages. This is based on some feedback we collected from R. So usually they are very happy with their R environment. The only thing they complain about is the scalability. So the thing we try to do is we try to get them familiar with the APIs, and then they can use familiar APIs but migrate to Spark very easily. And this is how we train a model in SparkR. So if you're an R user, and this is essentially the same as the R GLM methods, you specify the model, and you specify the training data, and you specify the family, and you get the model out. And we support, the most interesting part is the first part, and this is how you specify models in SparkR. And you can see this y tilde x1 plus x2 means you want to use feature x1 and x2 to predict the response y. And we support some common R formula operators in SparkR. And you can use interactions, and you can use just a plus or minus, and you can use dot in SparkR. The good thing about this is we implemented the parser in Scala, and then it's very easy for us to make this feature available to all language APIs, Python, Java, and R. So I want to make a quick demo here, and using the Databricks Community Edition. So you should get it maybe after today. And let's try to zoom in a little bit, or maybe too much. So in R, so this is R notebook. Uh-oh. So, okay, let's automatically attach. So everyone should know this IRLS data set. Oh. Okay, so it contains some variables here, and let's maybe create an R model. Maybe zoom in too much. Okay. Up here. Model equals to GLM, maybe just LM. And let's see what we want to predict. Just make it really simple. Maybe let's do this. And data equals to IRLS. And family equals to Gaussian. Oh. Oh, there's a typo here. And you get the model, and then you can call summary. Let me zoom in. And you get the model summary of the model you trained. And to switch to Spark, we only need to say, let's say df equals to create data frame from the SQL context and IRLS. And then we just copy the same code. But we need to make some little changes by changing the dot to underscore, because dot has special meanings in Spark. And we train the same model. Data should change to the new created df. And then we call summary. And you see it's the same process. And it outputs very similar model summary. You can get a good understanding of feature importance. And then, but we didn't implement all of them. We implement the most important ones, and there are definitely some to-dos here. But you can see how we want to make our users migrate to Spark really easily here. Yeah, let's go back. So this is how we use just GLMs in Spark. And let's talk about how we implement it. So first, this is a distributed environment. We store the records row by row. And in each row, you have the features, you have the weights, and you have the responses, and the data is split into partitions. And there are many options, and because it's a really classic topic. And we start with some stochastic gradient descent. And the first implementation is actually the mini batch version. Means you start by sampling a mini batch from your training data set, and then you do the gradient updates. But however, well, this is really not good for Spark, because it's not efficient for you to sample a mini batch, because Spark needs to go through the records one by one through the iterator model. And also, if you only sample a mini batch, actually you spend a lot of time on aggregating the gradients. Remember, the gradients are from each partition, you need to sum them up, and that causes some communication overhead. And then we can go with the batch gradient, basically increase the mini batch size to the entire data set. And it works, and it saves you some communication, but it's kind of slow in convergence. And then we switch to the second order methods. And like Newton's methods, it converges much faster if the objective function is good. And so basically, this is the update rule, and H matrix here is the Hessian matrix. But however, it doesn't really scale, because if you have, let's say, 10,000 features, and the H itself is 10,000 by 10,000, and that's very large. And people usually use Quasi-Newton methods in practice, like LBFGS or OWIQN. And we use both of them for logistic regression and linear regression. And actually, well, because they operate as a black box, as long as you can supply the gradient function to the solver, and it's agnostic to what kind of environment you are using, And we took the implementation, we called the implementation in Breeze. It's a separate linear algebra or math package in Scala, and just to take the best use of both projects. And after that, we also have the direct methods to solve the simplest linear least squares problems because it has an analytic solution. And we can actually solve the problem in one pass. And it's very efficient if you have a small number of features. That's usually the case for R users. And if the feature is less than 4,000, we can store a matrix of 4,000 by 4,000 efficiently, then it's good. Another benefit of this solver is you can actually provide R-like summary statistics in the output. That's why you see when I type summary in SparkR, you can see some R-like summary statistics. So on top of it, we can also implement this iteratively repeated least squares, and then it can solve arbitrary generalized linear models if you choose an exponential family. And essentially, it's just a linearized objective, and then iteratively calls the weighted least square to solve it until convergence. And it's the same feature sets, and you can provide summary statistics, but it doesn't scale to many features. And actually, this is the implementation in our core libraries. Oh, 2 minutes? Oh. So to help make our users really confident, besides this normal testing in our implementation, we also just verify our result against R directly. So this is a code snippet from our implementation. We put the R code you use to produce the results, and then we just put the expect vector to match that values and verify against that. So our users, you should be really confident about switching over to Spark. And there are a couple of tricks we did, and we don't have too much time to go over it. And one trick is to match R and R's popular package like a GLM net. So we just support options to do different kind of standardization or preconditioning to make the problem well behave and then easier to solve. And there are also some performance tips and we learned through the implementation, like how to handle sparsity, how to make the communication efficient, and how to just solve the numerical issues like this one if you want to compute log 1 plus exponential of x. And if x is super large, you just get overflow directly before you reach the log function. So we need to just take care of all those issues, and we need to take care of special handling on the transformation so we don't modify the input data because they're usually large. So there are some future work to do, and we want to get some easy handling of categorical features. Right now in R, you can use the model formula, but in Python Scala, if you have categorical features, you need to encode them first, then send it to the logistic regression or linear regression, then get them back. And we definitely want to just improve the support for R formula and then provide more model summary statistics. And we're also working on the model parallelism to increase scalability on the number of features. The current implementation kind of stops at maybe 100 million features, but we definitely want to go beyond that, like 1 billion. And there are also some internal performance optimizations we can use to call native kernels. So, and this is actually not the only implementation for GLMs on Spark. There are many other third-party projects, and I definitely encourage you to try them out. And if you found just good things or bad things, maybe just report on the user mailing list. And I will send the slides after my talk, so you can look at those projects. And yeah, that's it. So still have 1 minute.
Cool. Want to thank